You'll be so bored with this that you won't want to know anything in 2 minutes' time. Not from me, anyway. Fulcrum Engineering. Andy Ford speaking first. Brian Marks speaking second. They've worked together for over a decade, and the partnership tends to emphasise a holistic approach to building. It's not a case of sort of plugging in the engineering at the end. Okay, Andy will be focusing on low energy buildings, whereas Brian will be focusing on sustainable aspects of sustainable building and engineering. So after that long delay, and just mentioning again that the notes will be held with Belinda, so if you don't get the handout, you can get other copies if and when you need them. I'll hand it over to Andy Ford.
Hello, can you hear me? Can you hear me at the back? No. How do I switch it on? Hello? Oh, yeah. Right. In that case, I need to go up a bit. Hello everybody, can you hear me at the back now? Yeah. Great. Okay, I'm going to start briefly by introducing us. Brian's notes are not quite ready yet, but the sustainable bit will be there a bit later on, so you can get those afterwards. The first slide really sets about what we're about. We believe that if you build your buildings correctly, then you can have a low environmental impact. You can avoid complex buildings, and eventually you might be able to build in comfort. I'm afraid I'm going to start this evening with an equation. I'm not going to mention the equation, but I do need to get across a concept. And I'm not entirely clear whether everybody would know the concept. It's the difference between temperature and heat. If you see the top picture, there's a lump of something or other which is cold. There's a little candle with a label Q, which is heat going into it, and then it gets warm. And then a bit more Q goes in, and it gets hot. The temperature is whether it's cold, warm, or hot. The heat is how much candle you have to hold underneath it. That's absolutely vital in our branch of engineering to get that into your head. The other thing is a thing called specific heat, which is how much heat you have to put into a little block of any material to make it go up in temperature by a given amount of 1 degree C. Water is a particularly bizarre material, in as much you need about 2.5 times as much heat going into water as you do into almost anything else to raise it by the same temperature. So that's why it's used a lot. It's not just because it's a convenient wet thing. You can run down pipes. Another thing I've got to get across is the idea about heat rising. Well, heat does rise, but only convective heat rises. That is to say, things like gases and water, where the molecules can move around in them, then heat rises. So there's a little hot air balloon, and that's a convective thing. Heat goes up by convection. The other main way of heat transfer I want to talk about now is conduction. Now, conduction, it doesn't care which way it's going. It will go the easiest route. It's like going across a lawn because it's easier than going around the edge. It takes the shortcut. If a material is, say, metal, and you're holding that, a little hand is holding a metal thing across a candle, it won't take long before you burn your fingers. If that's made of wood or a good insulating material, it takes a lot longer and you probably never will burn your fingers. But that's important to realise that heat, by conduction, goes in any direction at all, including straight down. It takes the shortest distance between 2 points. If it's cold there, and it's hot there, it goes straight across that way. I didn't find out how to turn the slides on. So how do I do that? Thank you, Brian. No, that's not it.
Forward, that's reverse.
Oh yes, okay. Here we go. Right, where are we? Now I'm going to go through historically from about 1989 to 1995 through a series of jobs which started with the University of East Anglia, where we've been working since 1989 on about 5 different buildings. And the first one was the student residences, which are by Rick Mather. They're the curved block is Constable Terrace. That big black lump is the Sainsbury Centre. And there's 2 other funny sort of question mark shaped blocks, which are Nelson Court and one that was never built. So if we start with the residences, this is our first. Hang on, let me just move this. How do I get this to? That's no good. Forward. That's right. Yeah. Right. This is Constable Terrace. We were aiming here to build a building that packed a lot of people in. Each of them had a separate shower room, and each of them wanted a good view. Now, it ends up with is a building that's got a service core down the middle and all the rooms on the outside with a central corridor. It's been designed as a super insulated building. That's what it used to be called once upon a time. It's really just wrapping a very thick blanket around a building, and then right the way across the top, down the sides and underneath it, and then sealing up the walls so that you don't get accidental leakage. That is, drafts. It still leaves you with the windows openable. It doesn't stop air getting into it. It just says we're not just going to let the air creep in wherever it wants to. Having done that, then obviously if you want to keep the windows closed, you do actually need to ventilate it. It's got lots of showers, there's a lot of moisture going into the building. We considered whether you could do this naturally, and we simply said we're not going to take the risk, frankly. So we mechanically ventilated the building. And here is one of the student general meeting rooms. And it shows a ventilation unit. Just here is the ventilator. And it's a displacement ventilation system, which means that the air is brought in, it's blown down, and it comes into the room just a few degrees below room temperature. And if you do that, then you don't blow it fast across the room to mix it all up. You just let it tumble out. And it's rather like when you turn the hot tap on in a bath, the hot water goes straight to the bottom, and then it rises up. What happens with this is if you bring the air in at just below room temperature, it spills out and it gently spreads its way all over the place until it sort of fills up like a big bucket, gently filling up with water. And where there's something hot, like you, which is you're a hot bod, you're about 37 degrees C, which is really hot compared to room temperature. And you're giving off somewhere between 100 and 400 watts, depending whether you're sitting quietly or running around like mad. So when it comes to you, the air, there's a big pool of it, but when it comes to you, you're sitting in a stream of air which is rising past you because warm air rises. And it's drawing it from a cool pool of air. And it goes up to the high level, so above your head is where all the hot air ends up. It stratifies, and it's deliberately stratified. And then you take it out anywhere, you just have to get rid of it. So anywhere in that big pool of hot air, you can take it out, and you can almost put in the right amount anywhere in the bottom, so it's a big pool of cool air. The other thing this slide shows is low energy lighting. Now that means fluorescent lights actually, mostly these days. It's not all fluorescent, but fluorescent lights have always been a bit of a problem to a lot of people in terms of how do you make a fluorescent light actually a reasonable thing to have in your room. It's not exactly beautiful when it's stuck on the ceiling, but we've been trying to sort of hide the fluorescent lights, and you'll see as you go through these slides that we've actually been concentrating on almost coving lighting and lights coming from strange places. And I think it actually helps with the modelling of the room quite considerably. This slide is the junction on one of those question mark shaped buildings. It shows several things. Those things sticking out are shading devices. I'll come on to what they're doing later on. That little glazed link was a real problem because it's been made of single glazing. If you have a low energy building and you carefully insulate everything and you put in windows which are double glazed with sort of argon fill, low emissivity finishes, so you actually end up with all the surfaces inside the room being warm, and if you go and put in a cold single glazed link, all the moisture that's floating around the room suddenly thinks, ah, great, somewhere to go at last, and it will condense on that single glazing. So we didn't realise that it sneaked in, and the first year there was a load of condensation on it. Well, the other way of getting rid of condensation is to actually ventilate, so you put air through it. So that's what actually happened in the long run. We put air through to get rid of the moisture. But it's something to bear in mind. If you're going to do a low energy building and insulate thoroughly, you must do it thoroughly. You can't have bits where you don't do it properly. This is the section through the building. It started once upon a time as a 3-storey building and then grew to a 4-storey building. And you can see that it's double banked. The windows are kept to as small a size as is reasonable, and they splayed the edges so that light gets in. And actually when you're in the room, it still feels like the window's rather large, but in fact it's quite small. The ventilation system basically goes up through the centre, extracting air from the bathrooms. It's supplied again by a little displacement ventilator into the bedrooms. All the air goes together, and there's a little box at the top, ventilation and heat recovery unit. That throws the air out, but in the way of throwing it out, it catches the heat from it and puts it back into the supply air. It's not, as heat recovery, it's what it means. It's not a very complicated process. What it actually means is it passes the hot air past a plate, and on the other side of the plate of metal is the cold air, and if you leave it there going past, the heat goes through the metal plate into the incoming cold air and warms it up. That's heat recovery. There's nothing particularly complicated about it, but that's what it's doing. So it means that you can ventilate these rooms constantly with fresh air, but you don't throw away all the heat. You actually keep about 70% of it. This is just the plan. And this is the building in construction. You can see that, well, maybe you can't see, but with a bit of luck, if you look hard, you can see that the walls are double skin with 100mm of insulating material between them. That is about the minimum level of insulation that you could even consider as being well insulated. The floors are made of concrete slabs. The idea of that is to get mass into a building. And the reason for getting mass into the building is that when you sit there inside a room, and say the room has a carpet on and a false ceiling and lightweight false walls, all the heat that comes out from you and from any other heat source, such as this thing, goes into the air, and then it looks for somewhere to go. If it goes to the wall and it's a carpet it goes to the floor and it's a carpet, and the wall and the ceiling are lightweight, then it can't go any farther. It raises the temperature of the wall as much as it can, but what remains behind just raises the temperature of the air. It means it gets very uncomfortable. However, if you put big, exposed, heavy materials with plaster, say, I mean, you could have concrete floors, plaster straight over them, and then that is an exposed mass. What happens then is the heat that goes into the air gets as far as the ceiling and finds it's got somewhere to go. And it goes into that material, it raises its temperature slightly, but there's a lot of the material, and instead of raising the air temperature, it raises the overall structure temperature. And the amount of heat around is constant, so the air temperature remains lower. That was a bit sort of rushed, but I hope you got the general idea. It's the difference between temperature and heat. One last thing. When you're building a building, I talked about avoiding accidental air leakage. One of the main places where you get accidental air leakage is at the junctions of floors, ceilings, roofs. So, on all the buildings at the University of East Anglia, the top floor, where the roof sits on, has also got a concrete. It's just the same as any other floor, so that you can seal it properly around the edges. And then over the top of it, you've got a lightweight roof just to keep the rain off and collect it. Moving on. This is the second building we built there. It's by John Miller and Partners. It's called the Queen's Building. I should say John Miller and Partners were the designers. We are the engineers. It was for a completely different client. It's for the Health Authority. So, despite the fact it's on the University of East Anglia, we had a completely different client who'd never built a low-energy building before. The University of East Anglia had a low-energy policy, and we had to explain to their new client what that meant. It's also not a student residence where you're trying to keep rooms warm most of the time. It's an office building with lecture facilities and what else have we got? We've got a big gym in there, and there's lots of people going through it. And actually the problems are more to do with keeping it cool and comfortable in summer as much as keeping it warm in winter. Because we had a new client, we tried to stay fairly close to normal ways of building things, because the Health Authority are not exactly the quickest people in the world to progress. But so what we've got is a naturally ventilated building. That means in this case the windows open and close when you want to ventilate it. And that is something you really have to consider hard, because as well as the windows being a way of getting the light in and being a way of making the building look nice, they are also the ventilation system. And you have to think, who's going to control the ventilation system, and can they? I mean, if you imagine this room, which is now getting warm, nobody's going to get up and open the window. I can't imagine people will do that. I mean, that's not a normal situation when there's lots of people who don't belong, the room doesn't belong to them. They will not stand up and take control of it. But anyway, if they do, it's usually them sitting next to the window who gets comfortable, and other people don't. So it's very important when you're designing naturally ventilated windows to think through what it's like to be inside the building and whether you would actually get up and do anything about it. And then to decide how. So that it's got to be very obvious. And you can design very good naturally ventilated buildings just using windows, but it's best if the room belongs to somebody, so that they can get up, they know they want to change it for themselves, they can look out the window, they can see it's freezing cold outside, but it's hot inside, so they know when they open the window it's going to be cold air coming in. And that's their choice. On the sort of buildings where people don't own the rooms particularly, then you've got to sort of look at ways of making the thing stay comfortable anyway. And this is the lecture theatre, where we tried hard to provide an environment where people didn't tend to sort of just doze off. which is easily done. I mean, it's nice and warm, cosy, dark, it's easy. Now this one, shush. Here, the ventilation system blows air straight underneath a big concrete void, and then the air comes up very slowly underneath the seats. It picks up the heat, it takes it up to the ceiling, and you can see at the top it's got a coved concrete exposed ceiling. And that's what I was talking about. That's where the heat goes. It gets up to the top. It actually gets absorbed by the concrete. And firstly, the heat is taken away from you and goes up to the top. It doesn't get so hot, so it doesn't radiate great high temperatures down at you and make you feel boiling hot. It just slowly absorbs it. And it is quite refreshing. I'm surprised myself. Now, this is the other side of the building. You saw the drum, but this is the other face of it. It basically faces east-west. Now on the west side, sun rises in the east, sets in the west. Now, what you want to be able to do is control when the sun comes in. On the south face, that's quite easy. What you're after is sun coming in winter, giving you free heat, keep the thing out in summer so you don't get too hot. On the east and west faces, it's much more difficult because the sun's low in both winter and summer. But just in summer, it's more intense. So you've actually got to put something which you can physically go right down in front of the window. And here we chose to put the blinds externally with their individual rooms on this thing. So each person has a little light switch and they can control whether the blind's up, down, or shut or closed or open. And they seem to do it quite consistently. I mean, the only real problem with doing this sort of thing is that it's outside and eventually the wind's going to blow hard and it's all going to rattle like crazy. And then the manufacturers very sensibly introduce something to stop it destroying itself, which means they all shoot up. So if you get a really hot, windy day, then you're in a bit of trouble. So it all closes up, the sun pours in, but then you open the window. I don't know, I'm afraid, I can't remember. That's sort of natural ventilation. The other thing is you can see if you look at the windows, you can see that there's a little one to one side, which is a long, narrow one. That is a double window. You can either open it like this casement-wise or pulls out so you can leave it open, theoretically, during the night. That's because during the night the air's cool and it's nice to let it flow through the building and cool the structure down. That was our theory. Security and worry about people breaking in means that doesn't work. And that, if you want to use windows and use night ventilation, is an extremely important thing to consider, and we certainly do from now on. But this was a bit of a learning curve. So. This building here is not a low-energy building, but it's Keats Grove. It's a house by Rick Mather in London, Hampstead, and it's an all-glass conservatory. And the reason it's in here is because the glass, it's a north-facing conservatory, so I don't have any worry about solar gain. It's double glazed, fine, and the glazing beads are glass so that you can't see them. But it's mainly here because it's a radiant heating system. There's electrical current applied to these bits of glass, and they get warm. And indeed, they can get extremely hot if you wind it up full. But it's here because it's the next step along the line about learning how to make buildings comfortable, which is, instead of making the heat source a radiator or a warm air blower or something, where what's coming out is hot, warmer than you are, we were looking to try and introduce heat at more or less the same temperature as people. And this is our first attempt. It uses energy, but it's first attempt. So basically, if you make a large surface slightly warm, you can get out the same amount of heat as you can from a small radiator, but the temperature is close to room temperature. so that it doesn't feel hot. You radiate to it yourself, and heat is absorbed by it. But it gives a general feeling of warmth. I'll show you sort of later on where we use that much more extensively. This building is another one by Rick Mather, and this is Keble College, which has just been finished, although it was actually designed quite a while ago. And it shows rather nicely the effect of a good solar shading on a south-facing wall. The basement here, semi-basement, on this side, looks out over a nice grassy lawn, but it faces due south. And this is taken around about midday. You can see that the shadow completely stops the light, the sun, not the light. It stops the sun shining into the lecture theatres. So it means that in summer, the sun's high, shadow falls right across the window and prevents it going in. It also is rather an interesting design of shade, I thought. The main effect of this is that come the winter months, it doesn't stop the sun getting in, and those rooms benefit from the warmth. You can see again, it's from the other direction. This building is almost exactly the same brief as the University of East Anglia, and here we did a few things that we would have been better to have done at East Anglia, which is we used gas to heat it. There was reasons why we had to use electricity at East Anglia, which are to do with the cost of getting the central mains down to where the building was, and the fact there was no gas on the site. And what else was there? Oh yeah, we made a much better attempt at keeping the mass exposed. So the rooms during this heat wave we had, they remained remarkably comfortable. Whereas what happened at the UEA is, for various reasons, during construction, we lost the exposed mass of the ceiling because the contractor decided he was going to put in a nice false ceiling so he could distribute the services a lot easier. And it just got through. But we still kept the mass of the floor and the mass of the walls, so it didn't mess it all up completely. I lost it. Now, this here is a rainy building site, and not only is it a rainy building site, but if I can find the overhead, it's about how you might deal with keeping. Hang on, just a moment. Here we go. What is it? It's about an experiment on interseasonal storage of heat. You see that all wet bit on the floor? Well, what that is one of these. Oop, one of these. Sorry. Now, conveniently, one of the people who sponsored this building was somebody who manufactured polystyrene insulation. So the insulation came free. And we thought, well, great, we'll use it. So what we attempted to do, and this is really an experiment, and we're going to go back and see how it works, is to change the way that you insulate a ground floor. Normally, you would put the insulation down the walls and underneath the ground floor. However, what we've done here is it goes down the walls and then it goes outwards, away from the ground floor. And the reason for that is what I was talking about earlier. Heat doesn't just rise. If it's conduction, it takes the easiest route to the cold. And in this case, what we've done is the warm bit is inside, the cold bit is outside, so we've made it farther to the outside. So heat is now going through the floor and it thinks, I'll just nip under the wall and I'll pop out to the nice cold outside air, and it comes up and it thinks, somebody's put some insulation in the way, so it has to go farther. And when it goes, it has to go about, in this case, about 10 feet farther. And that introduces about a 3-month time lag. It takes about 3 months for heat to travel from inside to outside. if you kept a constant temperature difference. Now, there's a man in America called John Haidt who's done a lot of experiments and built quite a lot of houses. Most of them are underground houses, but by underground houses, what it actually means is sort of half underground, half buried, with lots of big windows. And he's done some experiments and shown that it takes 6 months for heat to move 20 feet. But if you think of it, 6 months is actually interseasonal. So it's changed from being summer to winter. So by the time it's gotten the 20 feet, well, there's no point in it going any farther. It's got to go back again. So it actually ends up, instead of the top room, which is a conventional underground house. I like the word conventional underground. Very good. Now what we've got here is instead of the shortcut to the surface, you've stopped it taking the shortcut to the surface by extending the insulation out this far, and it goes out 20 feet. So the heat merrily heads out underground, and then before it reaches outside, it's summer, so it goes back again. And because it's such a lot of it, it doesn't get very hot. It just stays more or less at the same temperature as the room averages at, which is about 21. So they measure the temperature underneath it, sort of 18, 20 feet out, in the middle of winter, and it's almost 21 degrees anyway. So you've got a huge amount of mass of Earth sitting there at 21 degrees C. And if you can imagine digging a big hole and sitting in this great big mass of Earth, you're going to be at 21 degrees C no matter what you try and do. So that's really what's going on at Cable College. Well, it's actually what's going on probably in the central... It's what's going on in the centre of the 3 lecture theatres, because the others are too close to the edge for it to really work. But that's what the theory is. And this is a man laying the insulating umbrella. It's a sandwich of insulation, polythene, insulation and polythene, so that the water doesn't percolate through and ruin the whole process, because what happens if water gets in, it dribbles through, warms up, takes the heat away because it's warmed up and it's gone somewhere. So we're hoping for success on that one, but we're doing other things later on which takes this a lot further. I'll move on now to the Elizabeth Fry building at the University of East Anglia, which is the most recent building we've done, and the one that I think is by far the most interesting so far. Let's quickly show you a section. Right. Now, this building it's 3 stories on one side and 4 stories on the other side. This is the south-facing elevation, and 3 stories the north-facing elevation. Along the basement, a series of 130-seat lecture theatres, which are accessed from the car park and the pavement by the car park, so that generally the students come from the main part of the university, walk along and go straight into them. You can also get down and through a staircase, but the general means of access is straight into the basement. And here we've got a lecture theatre again, which is a very interesting thing, lecture theatres, because there are a lot of people generating heat, with a lot of people needing to breathe, and they're very difficult to make them comfortable. And it's more extreme than most office situations, and it's more extreme than sort of the city lads actually, you know, with all their computers. It's more extreme in a lecture theatre than that. So it's a big problem. And here we've been using the ideas we did before, which is large, low temperature surfaces, using the thermal mass. So it's all concrete. It's actually, really, it's the University of East Anglia. There's a lot of concrete in that place, so it fits all right. But these are hollow core hollow core slabs. This is dense concrete block, and this is in situ concrete up to about here, and then it's slabs over there. So you've got a room which is basically a concrete bunker, really. But it's a very well insulated concrete bunker, and it's ventilated in the most unusual way. Let me see what's happens here. Right, so it's very well insulated. You see this. This is what the walls are made of. It's a concrete frame building, and it's got about 200 millimetres of insulation continuously around it. It's 300 on the roof. And the wall ties are nylon. That's to avoid cold bridging and reduce heat loss through it. It's about the most insulated building I've ever dealt with, and it ignores what's going on outside. We went into great detail this time to make sure that the building didn't have drafts and just air leakage going through it. So this is one of the details about how you actually build buildings so that it doesn't leak around the windows. It's the bits of polythene. You have to put the triple glazed low emissivity windows, and they're mounted in the insulating layer. So they're in a little wooden box and mounted on the inside wall, but project into the insulating layer, so that you get a continuous layer of insulation. And it is continuous. I keep stressing this. It's important. You don't give up on little bits. You deal with the details and get all the way around insulated. And then the polythene is clipped to the window frame and plastered in. So there's basically no way that air can get through it. But the building is very well ventilated. It's mechanically ventilated again. And in this case, it's ventilated through the structure. The idea of this is to actively change the temperature of the structure using available ambient conditions to do so. So, I've got a, let's see, again, it's a very well insulated building. There's a lot of people in it. The problems, in fact, are cooling it, not keeping it warm during winter. Let's go forward. It uses a system called Thermodeck, which is a proprietary Swedish system, which has been around for about 10 years in Sweden. And during daytime, it blows air through the slabs, which have previously been cooled. Now, I'll probably have to go forward one more, actually, so excuse me. Right, nighttime. Okay, it's got hot during the day. At nighttime, you use the available air outside, which is cool, to blow through the slabs to cool them down, so that come the next day, you've got a large, cool surface to cool the room down. And again, cool, but very close to room temperature. So maybe the slabs are at 20 degrees, so that as soon as the temperature in the room rises above 20 degrees, they're cooling. If the room temperature tends to drop below 20 degrees, they're actually a heating source. So it's sort of self-adjusting. It doesn't need complicated control systems. It just sits there, staying comfortable. And if we go back again, oh, I switched it off there. Let's try that. Oops. Oh dear. Sorry. On. There we go. Yeah. Which is backwards. That one. Right. Yeah. Right. During the day, ventilation just continues at a high rate. So you've got heat being radiated down from the slabs, or radiated back up if it's cool, and the air goes through the slabs, cools itself down, blows into the room. So you've got two things happening. You've got the heat being removed by the air and heat being moved by radiation to the concrete slabs. Right. Now, this is the airflow path within the concrete slab. me see. There's also a little picture. Look at that one. Better? Worse. That way around. That's it. Maybe I'll focus it. Never mind. Okay, so this is what happens to the air. It comes along from outside, from a heat recovery ventilation air handling plant, whizzes along, and then it goes in. The air coming along is in that blue duct, blown into the slab, into one core, and then that's it coming in here. And the red bit is where it's a lot of heat transfer going on. The blue bit is where there's not a lot of heat transfer going on. So it blows into one core, it goes along that core to the corner, and then at the corner it goes across to the next core, back again, across to the next core, and back again. And by the time it's done that, it arrives in the room almost at the same temperature as the air in the room should be, 21 degrees or thereabouts. And it's transferred all its heat to the concrete slab. So in winter, this acts like a huge, great storage heater. So during the night, you find out what they basically do is it's at 11 o'clock in the evening, you sample the temperature of the room and decide whether it's going to need heat. If it needs heat, you just turn all the boilers on, put some heat in until the temperature of the slab rises by a degree, and then you turn the boilers off. And the same thing in summer, if the slabs are too hot at 11 o'clock and the temperature outside is cool enough to cool them, you turn the fans on and just blow fresh air through them until they drop to about 20 degrees. Turn the fans off again. And it works jolly nicely. And I think it's the solution eventually to low energy buildings. This is a picture of another building, but this is the hollow core slabs being installed. This is actually one in the Middle East, where even though there's not necessarily available cool air at the temperature you want, although it's a hell of a lot cooler at night than it is during the day, you can deliberately cool it with a chilling plant, and it reduces the size of the chilled plant by a factor of about 8. And this is them lowering the slabs into position. This is how they make the holes in the slabs. It's a remarkably low-tech process. So basically a man comes along with a big diamond core drill, marks out where all the holes are for the air to get into it, and drills a hole. And then he pulls a screed, puts a bit of polystyrene in, or a little metal cap, and the structural screed goes across the top and seals it all up. And this is what it looks like inside. Here when you expose all the surfaces, it makes it rather tricky to move surfaces around. I mean, so you've deliberately made the ceiling solid concrete, and you haven't got any way of getting a light fitting on it. So we've had to go to getting the light in at the edge. And that's a coving, it's a simple reflector and a simple fluorescent tube to light the room. And then we've used that to distribute the surfaces, the same things. And those little round things along the ceiling is where the air is coming out of the concrete slab. This is the main entrance. That was the curved bit you saw initially. And the curved room is above the entrance. And this is the staircase going up through. It goes right the way through 4 stories. There's no heating whatsoever and no ventilation in this space. And in the middle of winter, it's quite comfortable. And it's still comfortable in the middle of summer, although right up by that roof light, it gets to about 36 degrees. The space below remains, mid-20s. This is just another view across at the end. And this is the boilers that heat it. There's 3 of them. They're just like the ones you've got in your kitchen. 2 of them are needed and 1 is a spare. It's a 3,250 square metre building. And let's move on now onto some other things that we're doing. And this here is by Warmby Cosden. It's a project for London Zoo that is still a long way from happening. But the idea is to build a tropical rainforest in the middle of Regent's Park somewhere. And the idea is to see if we can use the ideas of storing heat in the earth and in water, because it's a glass house, so there's an immense amount of heat going in. We're going to see if we can use those ideas to store sufficient heat so we don't need to put a big heating plant in to keep it warm during the winter. It's dying to have a go on it, but we need some funding, so if anybody's got any money from London Zoo. This is another building which again is following the passive annual heat storage theory, which is an underground building in Oyne near Aberdeen. This is by Edward Cullen's. They've just got the funding now, so we're off again on this one. And it's a visitors centre, and we're hoping to build this so that it needs little heating, shall we say. Maybe none. When we've actually got the building built, they might not use the heating system, but certainly it won't have a lot to start with. It may need some heating to get it going. And Brian will probably talk about what that means in terms of risk. This building here by Alex Durick is Eco Station in the Docklands. I think this one has almost got funding enough to build it now, but we're hopeful that if they will build it, it's a fascinating building which uses the exposed mass. We're trying to do this time the hollow core systems, but this time passively, with a stack effect dragging it through. And I'm really, at this point, I think I'll probably hand over to Brian, who's going to talk about sustainability and plants and compost and the like. So, Brian, over to you. Can I just transfer this?
Hello? Hello. Right. We're running a bit short of time, so I'll have to rush through this a bit. I want to talk about the other aspects of sustainability that apply to building construction and servicing them. Sustainability is a wonderful term, splashed around everywhere, and is on the verge of entering legislation, basically on the back of the Rio Convention. It's not been taken up in terms of enforceable legislation yet by hardly any government, because it's a worry to central government. Sustainability is the ability of something to maintain itself, and it must have considerations in it of no great growth, which worries governments, because growth means you use a hell of a lot of stuff in and you produce a big pile of crap once you've finished using it. So you have to limit growth so that you limit how much comes in, and you therefore limit how much comes out, and it's possible to carry on doing what you were doing for much longer. That effectively is sustainability. It's a function of taking responsibility for what goes into your building and also what comes out of your building. Low energy design is one aspect of taking responsibility for what goes into your building. And I want to talk about some of the aspects of taking responsibility for what comes out of your building as well. Before I move on to some of the specific systems I want to talk about, I want to cover how this as a concept influences design and the actual design process. We are engineering consultants. We are not lobbyists. We have a duty of care to our clients to advise them on the most appropriate solution. You've got to hold this word appropriate in mind all the time. Although sustainability, low energy design is important, the solution, the design solutions that are chosen to deal with it have to be solutions that are appropriate to the building, to the position of the building, and most important of all, appropriate to the building user and the lifestyle of the building user. If you attempt to shoehorn a solution into the building that depends on your client opening the windows at exactly the right moment, it will fail. When it fails, it will fail catastrophically. Probably the building will be designed so that to fix it involves draping cables over the ceiling, crashing pipes through walls, and you'll end up with a horrible building. So it's absolutely essential that the client and the building users and all the design team are with you all the way and understand the process at every step and agree to the process at every step. There is a use of the word holistic when it comes to sustainable or green design. It's a very important concept and the words are overused. It's a great word, I use it all the time. It's necessary to use it because you're attempting to influence all of the aspects of a building. You're trying to influence the structure. Andy's talked about the necessary use of thermal mass. You're attempting to influence, to the advantage, the form of a building. Andy talked about thermal stack effect. Thermal stack effect needs height, needs concepts like chimneys. You're trying to cut down your problem in the first place. That means you have to consider the aspect of your building, the orientation, which way does it face? We talk about windows a lot. Windows to us are a piece of ventilation plant. But they are still windows and we have to design them as a piece of ventilation kit in conjunction with the architect who's interested in the aesthetics of the window. And very importantly, we have to design them in conjunction with the user to make sure they'll actually use them. Because if they don't use them, the building will fail. And so when you are attempting to design, I'll call it sustainable, it's essential that the design team and the client get together to openly discuss all aspects of a building and its construction, and to an extent you have to disregard the traditional boundaries between the disciplines, because the concepts we're talking about will run throughout the disciplines and everybody has to move together in concert. Older ways of involving engineers like us have to break down. Years ago, we were only ever brought in once the building had been designed. There wasn't enough duct space shown, there wasn't enough plant space shown. We were given the building and told to service it. And that, to an extent, was fine when everything was done with pipes and wires. We could squeeze the pipes in, we could squeeze the wires in, and we could make the building work. If we were given the building early enough, we could make it look like something. If we were given the building too late, then you ended up with the pipes and wires draped everywhere. It's impossible to design green, to design sustainable with that kind of late involvement. Everybody has to get together right at the beginning and they have to get together with the client. And all disciplines have to evolve the brief together. The briefing process is essential because you need to know the abilities of the lifestyle of the building users to cope with constraints that we as designers may be thinking of putting on them. We have to know if they are going to open the window at the right time or not. We have to know if they don't open the window at the right time, can the facilities manager or the building manager go around and slap their wrists and say, well, no wonder you're uncomfortable, start opening the windows properly. How can people be expected to do that unless they've received education in what they're supposed to be doing? And so the briefing process is absolutely fundamental. There is another aspect of the briefing process that should be mentioned, and that's risk analysis. Nowadays, like our practice, has relatively sophisticated and powerful computer simulation models that we can plug in numbers to work out if those arrows that we draw on drawings, if it actually does do that or not. But these models at the moment are powerful, but are incredibly expensive to input into, massively expensive in engineers' time. You have to be very careful how many options you analyse on this basis, because the number of options to look at in terms of crunching the numbers, as engineers do all the time, on a free-running building, a sustainable building, are huge, because you've got our normal options, which are day, night, summer, winter. You've also got to consider options about how the occupants are actually going to behave. How many of them are going to be in that room? Sometimes there's going to be 10 of them, sometimes there's going to be 100 of them. Patterns of usage change continuously. We have to analyse how this particular pattern of usage would work if it's cold at that time, how it would work if it was hot at that time. So you're continuously taking different parameters and laying one on top of another and trying to analyse it. Well, the answer is you can't. We can get quite close nowadays, but the idea that an engineer can sit down and work out exactly what will happen is probably fundamentally false. We can't. We're very, very good at guessing. We're very, very good at applying experience. And we are extremely good at adding margins. We add margins to make sure it works at the end of the day. But if you lob on a margin of 50% onto something, probably you didn't need it. We're covering our backsides. We're trying to stop being sued, and we're trying to make sure it works. But if you are really going for a sustainable building, you don't do that, it will be a waste. So what are the alternatives? The building has to work. The building has to comply with the normal criteria, design, cost, blah, blah, blah. If you have a £10 million building, it can afford quite a lot of R&D in the design. And so maybe you can actually analyse these various options and come out with a finely engineered solution that you know will work. So you had a £500,000 building. The total fees on the project are going to be, well, £500,000, probably £70,000–£80,000 for everybody, all disciplines, architect, engineers, quantity surveyors, project managers. In that lump of money, there is not enough to analyse the hell out of the building. We, however, can say, in our experience, this solution, which we will put forward, stands a very good chance of working. We might say stands a fair chance of working. We might say stands a tiny chance of working. But provided this is discussed openly with the building users and the client, and informed consent is given by the building users and the client, it can still give rise to a successful solution. The reason I mentioned risk analysis is that we should, as engineers, attempt to tell our client what risk we feel of a solution which is intentionally designed close to the bone because we want to be sustainable, what risk there is that it will fail. A very difficult thing to analyse. There are, however, arrangements that can be discussed with your client building user which will allow this risk assessment to be a bit rougher. We can propose solutions which, if they fail, have a fallback position. For instance, Andy was talking about the Archeolink building in Scotland, how we think it might not need any heating at all. If we approach, well, the approach we take to the client in a building like that is to say, we think it might not need any heating, we think there's a chance it will need some heating, so how about building in a contingency that if heating is necessary, it's a very, very easy thing to add after you have allowed the building to operate and can take a decision based on fact. This creeps into a lot of our designs for that reason. A lot of the passive cooling designs may absolutely do away with the need for active refrigeration, but we always hold in mind the need to have a contingency design. So we will have a bit of the building which is sited so we can put the chiller on it. We will have arranged the electrical supply so it's a matter of just plugging into a plug to give it its power supply. We'll arrange pipe routes so you don't have to tear up the building to put in chilled water if you end up needing it. It's an important concept and is underused at the moment. The other part of the design process I want to mention is the bit when the client moves in. This is called, well, immediately prior to the client moving in, is called commissioning. Services installations have a commissioning period. They're always too short. They come at the end of the construction period. The client, building users, hammering on the door. They want the building. Everybody wants to squeeze that period except for us, because we know how important it is to let the systems run so that you can tweak the controls and make them run the way that we expected them to run in design. There is a problem with constricting commissioning periods for standard building service installations. Once you move into a holistic, sustainable design, you're trying to commission the lifestyle of the users. It's an integral part of your design. And the commissioning period, therefore, is not only that 2-week period shown on the programme just prior to handover, it's probably a year of the building being used. And it has a cost. And it has to be overseen by someone who knows what they're doing. It has to be overseen by someone who, if they see the building being used wrongly, can influence it and put it right again. And that cost has to be shown when you put forward an option to the client. It is part of your design. It's part of the capital cost, and is important and cannot be discarded in the way that it is nearly always discarded now. No one's paid any fees to do that when the building's first occupied. We scratch around trying to tell people what's wrong if something's wrong. Same with it. The architect will do the same thing. But there is no sum of money set aside for proper commissioning with the building in use. We hand it over, we've done the snagging list, tend to come back in a year, do the end of defect snagging list, everybody waves bye-bye and hopefully everybody's been paid and are happy. It needs more than that if you're going to go for a holistic, sustainable approach. I've talked about sustainability being taking responsibility for your inputs and your outputs. To do that, the first thing you really want to do is to reduce your need for inputs, which will quite possibly reduce your necessary outputs. So, firstly, look at the design. If you want to take this route, look at the design, and rather than leaving yourself with a problem that has to be dealt with, reduce the need for things. Design intrinsically low energy, so you don't have to use a lot of energy. That means you're not paying a man to pollute several hundred miles away on your behalf. When you use electricity, that's what you're doing. You're saying, I like electricity because it's nice and clean. I know it costs a lot, and I know it's not very good in terms of conversion of energy from raw energy into the stuff that actually comes out of your plug. But the reality is you're using it in your building and it's all lovely and clean and all you've got to do is pay your electric bills. What you're actually doing is subcontracting out pollution to somebody else who's doing it on your behalf. They're generating electricity from the power station through the distribution mains at around 30% efficiency. If you use a gas-fired condensing boiler to heat your building, you quite possibly are using gas at an overall efficiency of 85%, sometimes 90%. If you took the choice to use electricity, for a start, you're only by the time you first buy it, it's only 30% efficient. Then you do things with it, adding even more inefficiency to it. So you have to bear in mind who's polluting where. You take responsibility for your building. So you have to think of what's hidden inside buying things. As I've stated, you have to consider the aspects of lifestyle change that your design may, by implication or overtly, be requiring. Some clients just cannot change their lifestyle. If you're a city dealer, they won't do anything except turn on a light switch, and they have to be comfortable. It's virtually impossible to persuade anyone that they can do anything other than that. Your commissioning client will say, we can't afford for them to get up and open the window, it loses too much money. Talk to your client about the reality of statements like that. When you are talking to your client, one of the important things you'll be talking about is how much is it going to cost. Cost is a great way of making a value judgment. That's mostly what we use it for. We say, that is better than that because it does the same job and it costs less. But actual cost is only a shorthand for value judgment. There are other aspects to value judgment, some of which are not overtly costed. For instance, if you use electricity, which I stated before, what's costed is the price of electricity to you. That's great. But when you use the electricity, you're actually subcontracting out someone else who's going to produce a huge amount of carbon dioxide, some sulfur dioxide, some nitrous compounds on your behalf, is going to chuck them into the atmosphere. The acids come down as acid rain, the carbon dioxide adds to the greenhouse effect, gives rise to problems. Those problems happen, and the taxpayer, effectively, or the world's taxpayers or the world's people, pick up that side of the tab for you. You have therefore subcontracted that out, and the cost of your waste is being hidden. And you have to, if you're taking a true value judgment on a sustainable concept, you have to attach a value to your waste in all its forms. It's very important to understand your client's attitude to money, to capital. Some clients will take an entirely different view on money to other clients if they are valuing other aspects. They may well value the PR aspect of being seen to be green. That's worth cash to them, and you can start showing it in your options appraisal when you're deciding we can either do this or that. And you have to talk to your client about how much do they value the PR of being green, how much do they value the marketing possibilities of having green packaging to show that they produce this item in a green factory. Some clients value educational aspects of design, and it's value in the same way as the running costs are value. It's all to be considered together, and you have to come up with a way of combining money with other value judgments. You have to talk to your client about value judgments generally about the environment. There is a concept of prime energy, which is the actual energy used to produce the energy you think you're using. So the prime energy ratio of electricity is very bad because it's only 30% efficient to produce in the first place. Whereas the prime energy concepts of gas are much better because you just get the gas and use it directly in your installation. It's not necessarily reflected in cost. You have to get from your client an ability to take the value judgment for them so that you can include it in your analysis. Another aspect that you have to talk to your client about is embodied energy. Embodied energy is how much energy does it take to make something and deliver it to where you want to use it. So it's how we look at, is concrete better than steel, is better than brick, is better than wood. Steel has a pretty bad embodied energy level. Takes a lot of energy to make a bit of steel. Takes less energy to make an equivalent strength bit of concrete. Takes even less energy to make wood. That's great. Partly it's reflected in the cost of the materials because obviously the producers have to value the energy, but quite often it isn't. You need to get from your client how important do they feel that is, because as I said before, we are consultant designers, we are not lobbyists, and we need to put forward an appropriate solution for our client. I'll now try and whip quickly through what comes in to a building and what goes out. What comes in, as far as consultant service engineers are interested in, is energy. As I I've said we try and design to reduce the amount of energy we need, but once we've established our minimum appropriate energy need, we can say, well, can we get this energy in a way that is sustainable, in a way that where we can continue to get hold of this energy without hurting anywhere else. These are the aspects of sun, wind, geothermal, ambient energy sources. That's what they are. They're energy sources that you can grab hold of without hurting anybody. There are discussions about what not hurting anybody means. Lots of people don't like wind farms. They feel that the low-level sound is hurting them. They feel that the aesthetics of a wind farm is hurting the actual landscape. These are to be valued as comments. I'll put a couple just to slide up, just to... Sorry. Here's a totally confusing overhead. It shows some wind turbines. It's actually to give you an idea of what a windmill can do. This windmill here is a 3.4 metre diameter sail. That's big. 10 foot. Not many buildings could get planning permission for anything much more than this. Pretty rare sight. But you'd think, well, 3.4 diameter, that's a really chunky windmill. You'd especially be interested in the fact that it's going to cost you, you can see some of the costs are up there, I left them on purpose. Once you tot all your bits up, you're looking at a cost of probably 6,000 quid for that thing. Now look at this, you can't see this curve up there. In fact, you can't see it at all. That gives you the actual power output of that windmill against wind speed in miles per hour. It's essential, before you embark on a design that involves, and I'll call them alternate energy sources, or non-polluting energy sources, I think is actually much better, to do a full survey of your site. What have you got to deal with? Because if the average wind speed is 6 to 10 metres a second throughout your site, that windmill there, which looks big, has cost you 6,000 quid, will produce enough electricity to light 3 decent electric light bulbs. You begin to get economies of scale as you get bigger. But as you get bigger, it's impossible to incorporate it in your building. I wanted to put this up because there's a lot of discussions about, oh, let's have a windmill. It's going to cost you a lot of money, and it's not going to drive your lift. It's not big enough. It's very difficult to store electricity. You have to use batteries. Batteries are very expensive. They're environmentally unpleasant to produce. You have to apart from a bit of battery storage, which you can feasibly allow, you have to use electricity when it's produced. There are other methods of alternate non-polluting energy source. Something that comes up increasingly is photovoltaics. This facade is covered in photovoltaic panels. At the moment, we're actually being advised by the government, and partly advised by the photovoltaic cell manufacturers, not to use them yet because they're too expensive. Per kilowatt hour produced, they cost a lot of money to buy. However, research and development on alternate energy sources is being focused on photovoltaic panels. As you can see, they can be incorporated into the structure of the building and still produce an attractive facade. Well, that's open for discussion, but in that particular one. It is expected that in 10 to 15 years' time, the capital cost of the panel, given the output of the panels, given it's Britain, Britain is not very sunny. You obviously do better with 1 square metre of panel in Australia than you do in Britain. It's expected to, in 10 to 15 years' time, the cost will have dropped to the point where it is the most appropriate thing to do. And we are eagerly awaiting the time when they are cheap enough to use, because they truly are non-polluting. Once you can get used to the aesthetics that they generate, there is no other harmful byproduct. There's no noise. There is very little that anyone can in fact take exception to, except possibly from the way they look. Other aspects to consider of alternate energy sources are active solar installations, where you basically just take the heat out of the sun and push the heat into your installations. I haven't really got time to go through the various types of this. They are a very good idea. The only trouble is, in Britain, they give out the greatest heat when there's the greatest sun. There's the greatest sun in summer. In summer, we don't need any heating. So you're basically looking at other requirements for heat with solar installations quite often. Sometimes you certainly can effectively incorporate them into a heating scheme, but you are on far safer ground if there is a summertime heat requirement that you can use them for, because their output will be so much greater per square metre, i.e. so much greater per unit cost. Another aspect of alternate, it's not really an alternate energy source, it's just a sensible way of hooking together normal standard pieces of kit, is called combined heat and power. Combined heat and power should be considered along with alternate energy sources, because it is a method of effectively, you take a generator, diesel generator, gas generator, and you generate some electricity, and you use your electricity, and the inefficiencies of production are heat. You take your fuel, you get your 40% efficiency, 30% efficiency from your generator. What makes up the rest of the inefficiency is heat. Heat comes out the water cooling jacket, heat comes out the flue, heat comes out the actual engine, the block. If you can find a use for your heat, that heat is free, because the central grid only generates a 30% efficiency anyway. So if you can have your own little Jenny, it's still doing its 30% to produce its electricity, but you then have, call it, free heat. So if you have this, at the same moment, a requirement for electricity and a requirement for heat, you can marry the two together and you end up with a very efficient overall system. But it takes considerable analysis of what's actually going on in your building, because electric use cycles are somewhat different to heat use cycles, and you're trying to overlay the two along with the actual lifestyle of your building user. The other, that's really all I was going to cover in terms of inputs, which are energy. I now go on to outputs of energy, outputs from a building. Waste products from a building are carbon dioxide from people and from the energy usage, because nearly all energy usage involves oxidation of carbon. We burn a lot of carbon. It's how we get hold of most of our energy now. Obviously doesn't apply to nuclear power, which has its own problems. So we produce carbon dioxide. We produce general non-organic rubbish. We produce organic rubbish. People leave their pizza crusts, you've got to do something with them. We produce faeces, urine, mixed up with toilet paper. And we produce wastewater. We have to, in a sustainable development, consider how the building and the building users can take responsibility for those products. Carbon dioxide, we are saying you can take responsibility by building a low energy design. General non-organic rubbish, the only way that a client, a building user, can take responsibility for the general non-organic rubbish they produce is if they've got room to take responsibility for it in. So you have to have, when you design the building, you have to have a space where the poor people can separate the various horrible things that they produce, so that the paper can go to the recycled paper store, so the glass can go to the glass store, so the metal can go to the metal store. It's useless if all you've left is a little slot under your work surface where they have their one bin. They can't do it. You're taking away any of the opportunity they would have to take responsibility for this, even if they wanted to. So we have to facilitate that. Somewhere I've got a crappy slide, in fact. That's actually what we've got at home. It's really simple. It's actually some 4-inch UPVC drain pipe taken through the wall. There's a little hinge, there's a hinged tile in our kitchen that leads into each one of those. It's just got a black plastic bag. So we don't have to keep it in the kitchen. It naturally sorts itself, and it's done the storage in space which isn't at a premium. I actually have another slide. That's the rubbish that my family produces in a week. The only bit it hasn't got is it's only got 1 day's worth of organic waste. That's in that little Tupperware container at the bottom. It's ever so nice to compost organic waste. You turn something which has a cost to dispose of, is capable of causing severe environmental damage if disposed of in a landfill site, into something that actually you buy from the garden centre if you chuck it on a compost heap. You can't have a compost heap unless the building's been designed to give you a potential space for one. And so it has to be discussed with the client at design stage. This can apply, it's not just domestic dwellings. This can actually apply to commercial, industrial. It obviously becomes harder, and you have to do it in conjunction with discussions with your client. The next aspects I want to run on to is one of the other waste products which fascinate the British, which is faeces and urine. I'll take this off. I'll put up a... Here is a slide. Did you focus this thing? give up. Yeah. Has it?
On the red knob.
On the oh right, brilliant. So this is just a selection of different compost toilet designs. There are hundreds of them. All of them have their pros and cons. But fundamentally, what they seek to do is to collect the faeces and the urine, to allow it either to compost under the toilet itself as part of the unit, or in some other designs, I think there's one up there actually, which generically are called crap in a bucket designs, where you actually crap in a bucket. A very nice bucket, very well designed bucket, very well sealed bucket, or ventilated while it's in the toilet, and once it's full, you put the very nice lid on your very nice bucket, take it out and pour it into a central composting unit. Similar to a thing like this, only it sits outside in the garden. It's insulated, takes about a year. Within a year it will be composted, and it will the pathogen content will have reduced to the point where it is safe to use on the land. When considering this type of waste treatment facility, you have to bear in mind that what is going on at the moment. What's going on at the moment is this great arrangement where we get drinking water, we mix it down with crap and urine, we send it through